again, of unnecessary sharing. Because there's many cases where the number of threads that are runnable, certainly from the machine, but if the number of threads is runnable larger than the number of cores, then there's not really a reason to actually have a shared queue, right? Because every process is going to be busy anyway. And so the right way to structure this is something that we call a Trojan called per core data structure, or per CPU data structure. And the idea is very simple. Instead of having one local queue, you maintain one queue per processor. So each processor has a queue pointing with runnable processes on. These queues can be protected with per core locks. So here you can actually have those little lock on it, L1, L2, etc. And so, as long as every queue, as long as there's a lot of runnable or a lot of threads in the system, there's a lot of work to be done, then presumably it's going to be the case that every core, like every scheduler when it runs, look in its local queue, take a local lockout, and run through it, dust, whatever it needs to do, find a process to run, and it runs it. Right? And we saw last week, right, that per core, uncontained locks are actually very inexpensive. So it's perfectly fine, to have a per core lock, right, which is mainly used, by the process that actually is maintaining and managing that particular queue. Right? Now this really has one downside, right? Is that if the load is imbalanced, for example, all the runnable threads actually happen to be in this queue and none of them happen to be in that queue, and then we're not going to get good, efficiency out of our machine, right? And so the typical way, of course, to play the game is to say, well, as long as the thread's in my queue, no problem at all. I can do everything local. But if my queue actually happens to be empty, then I'm going to look in other people's queues. Right? And then there's typically called work stealing. Many algorithms for it, and we're going to talk about that. But the idea is pretty simple. If it's only the point that actually really have to share, you're going to go share. Which is mainly the point that you're actually have nothing to do, and you need to find out where somebody else's work is. And in fact, if you share, you don't really have to go all queues, right? You can go core by core. You're going to find the first core that actually has a lot of work to be done, and you do that. Of course, the reason you have to have these locks, right, is to make sure that when stealing happens, that the stealer also can acquire the lock and actually run atomically through that list. But only in that case, there's contention on that lock. And we see maybe only contention with one by core, as opposed to many. Does that make sense? So this is the game, basically, this is an example. I think this is the game that basically operating system kernels do almost for every data structure in the kernel. You're going to go through a technique that basically, just per core data structure. Okay, go ahead.
So it's when, in this whole work stealing strategy here, if there's a bunch of, say there's a bunch of threads in the queue for one core, and not very many in the other core, but they still never get empty, would that be a little unfair because the threads in the bigger queue wouldn't get as much time?
Yeah, so the way that Linux is addressed, for example, is you do like every larger unit of time, you do a little bit of load balancing. And you run a load balancer, and that moves basically, if some queues are twice as large as your queue, you take half of that work you put in your queue. And so over a short, maybe imbalance in a short period of time, but then over a long period of time, it will actually work out reasonably well.
Okay. Does it compensate? So if you were like in a really long queue, it would like put you into a shorter queue?
It could. I don't think well, I shouldn't say it would actually the current algorithms of the day because the algorithms change continuously, but no. And again, I'm going to talk about this. We're talking about work stealing like 30 seconds. Turned out, like on any topic we're talking about, there's a whole literature on this. About what is the best work stealing algorithm, how do you do it, how do you manage it? All these questions like should you compensate for people that actually were in a long queue and blah blah blah. Huge amount of stuff. To me, the main point though that I want to hit home here is that this is sort of an example again where what's a shared queue, the queue is always sharing. Not really the reason to actually share it always, so you can sort of eliminate or unnecessary sharing by actually going through a core strategy. Make sense? And so if you look at the Linux kernel, you will see this strategy applied over and over, and the evolution sort of getting more parallelism. This whole sort of technique is being used. So now, if you take the extreme point of view, right, saying like, well, I want to avoid, as sort of earlier, you want to avoid this sharing, just don't share at all. Right? And so the extreme point of view is to say, well, great, we have enforced, we just run n kernels on that. Right? Each kernel manages one core or one processor, and that's it. It's just like a distributed system. Right? And so there's, at that point, like, we're all done, don't scaling bottlenecks, because, there's no sharing period. And each kernel can operate, totally independent of each other, and bingo, so problem solved. And in fact, there's a bunch of research, that explores operating systems that are built in that kind of style. Barrelfish, Fox, the operating systems where they take what they call multi-kernels. Instead of having a single kernel, you have multi-kernels, where every kernel and every processor works independently, and basically you treat it as a distributed system. And of course, it works fantastic on machines that don't even have shared memory. If you don't have shared memory on your machine, then basically that's the obvious place to go because there's nothing to share. You don't even have memory to share. So why have any sharing? But you definitely go to a multi-kernel. Right? If you do have shared memory, it's sort of a little bit of a bummer, right? That you're basically giving up on it by saying, we're going to run everything independently with each other, no sharing period. And yet you have the shared memory sitting there, right? And particularly because you truly do like work stealing, you do like load balancing. It's nice to have a shared buffer cache, right? If you do a pure multi-kernel approach, where do you stick the buffer cache? Somebody, presumably, you don't want to read the same file from disk, in every core kernel, right? And that seems like a waste. So it'd be nice to actually, sort of this trade-off, between you can go through the extreme road, with absolutely no sharing, but then you sort of run into this general problem with operating systems that the reason actually you have to share data structure is to do research management. And then you push everything basically one level up. Right? And you can, in the distributed system, you also have to do research management. So you can build a distributed scheduler, correct? That actually does work stealing in a distributed manner. And not take advantage of all shared memory. Most machines actually do come with shared memory. So most of the lecture is going to focus on actually on the assumption that you do want to share, and that we basically have shared memory. If you're interested in these other architectures, there's tons of papers you can read about it. All right, so we're going to go down the road of shared memory, and we do want to share data structures, and we're going to sort of investigate really this technique of like using third-party data structures. And this is sort of like in the main operating systems of Linux, FreeBSD, OpenBSD, Windows. All go down that, all are in this sort of camp. Okay, so this is the main approach. Okay, so let's look at a couple other. So, in some ways, the stepping one is a little bit easy, right? Because there's so much, there's not much sharing going on. The only case when you share it, when your queue is empty, or you want to rebalance the load. So those are rebalance the load is not sort of really time critical operation. Stealing, when you're empty, is important. But there's a reasonable, there's some sharing going on, but there's not a huge amount of sharing going on. So let's look at a couple other cases that have a little bit more feel for what it takes to actually get parallelism basically going. So another, I think, obvious good place if you want to use sharing is like buffer cache or any type of cache. Whether it's a name cache, almost all kernels have a name cache for the directory, a buffer cache for regionally read blocks and all that kind of stuff. And so the typical organization, the typical data structure that an operating system will use is a hash table. So you're going to think about a project. I don't know the buckets in it, right? The key value cache. And we saw this in one of the earlier homeworks, if you remember from the beginning of the term, a long time ago, where you did sort of look a little bit at parallelizing lookup in a hash table, when we looked at basically when we looked at p-frames. And so let's look a little bit about like, what it would take sort of to avoid the necessary sharing here. Right? Clearly, we want to share buffer cache because one core already looked up the name. We don't want another core to do all the work of opening the file or going down the directory tree and all that stuff. Right? Or going off, even worse, don't issue a disk operation even though the page is already in memory. So what are the techniques? Well, sort of a little bit in that assignment. And, the first assignment solution, solution one, is use a lock to protect the whole data structure. Right? One lock. Right? And so there's a quantitative lock here. If you want to do anything on the hash table, you grab the lock, you do your hash table operation, you release the lock. Right? And again, you might think, well, that's pretty good. Right? In fact, most operating systems sort of started in that way. Because how many instructions does it take that you want to look up in a hash table? Well, a mod operator can find the slot, right? And then, or whatever, a couple operations will run down this queue, right? And if it's a good hash table that's appropriately sized, this queue is going to be short, right? That's the whole point of the hash table. So it's not a ton of instructions. Right? So the critical section is reasonably short. But, as we said before, right, last week, if this lock actually happens to get contended, right, we know that then the performance can get really, really quickly. Right? Because the extensive part actually is in probably getting hold of this lock, moving the cache line, which is hundreds of cycles, right, from one core to another core, and then run down your cache. So we want to do a little bit better, and I think in the assignment we actually start this solution 2. So solution 2 is to say, well, reduce n locks, and one per bucket. Right? Here lock, here lock, here lock, here lock, here lock. And presumably this is going to give us more parallelism, right? Because we do that, whatever, we'll take the key, right, that we're looking for, we modulo to something. If the keys are randomly uniformly distributed, there's going to be 1/10 chance that we'll end up in the same bucket, right? With a bit of lock, we're in different buckets. So that means we're going to hold different locks and we're going to run around different lists. And so presumably, there's less contention going on because we're going to spread the load across all n locks. So this seems a pretty good solution. If there's something you want to maybe do even better. Because there's sort of still a little bit of a bummer, because if we do happen to happen, we hit the same bucket, then both of us are going to run down the bucket, right? And then we're going to hold the lock. One is going to hold the lock, and the other guy is going to run through it. But we have to expend sort of moving that lock between us. Right? So the next step in aggressiveness is to say, well, no locks. Free. No locks. Still block free. Right? And then the stuff gets pretty hairy very quickly, but that allows you to at least get rid of the possible contention of the lock. So one way is it turns out that there's a whole literature again. It's going to be like the same story for most of the integrated lectures, but there's a whole literature on lock-free data structures. And maybe some of you have taken one of the parallel programming classes or Shavit's class. And operating systems today basically go through the trouble actually of using lock-free algorithms. Because the number of cores is large enough that actually is starting to become important. And you sort of see this evolution to that in Linux where you start out with one lock, then you go to n locks, and then go to lock-free. Make sense? So what we want to do is take a little bit of a look at what would it take to actually remove this last lock by using a lock-free list. I'm going to make it a little bit more simple. I'm going to just use this list as a queue. Right? So you insert things in the beginning, and you delete things from the beginning. And then that's the only thing you basically do. Or you look and you run through it. So the way you implement objector on. So a little bit of fragment of code that shows you a lock-free stack, basically. I don't intend that you'll be experts at lock-free programming at this lecture at all, but just to give you a little bit of feel of what the issues are. fact, this is a kind of code that basically nobody should write because you get it wrong. It's very easy to get wrong. I mean, think about all the code you've written so far. This is like an auto order of magnitude more complex in terms of reasoning that is correct. So the first thing is if you're attracted by lock-free programming, the first thing to do is not do it. Keep your temptation under control. Then learn, if you still want to do it, learn a lot about it, and then maybe you start doing it. And of course, this is a little bit of a mean or strange advice because people that write operating systems, they have no choice, right? There's going to be somebody who has to do that lock-free programming. Now, generally set up in a way that very few people do it. Most of the kernel developers in Linux don't do lock-free programming. There's only sort of a handful that sort of the official stamped experts of lock-free programmers, and those are the people that inspect all the changes and make sure that everything is right, because it's so easy to get wrong. And of course, if you do a good job, you encapsulate it in nice abstractions that somebody writes this clean abstraction, like whatever, right? Concurrent hash table, everybody uses the concurrent hash table and doesn't have to think about lock-free programming, except for the poor guy, right, that actually has to implement the lock-free hash table. Okay. All right, so, okay, so there's a, don't let yourself be misled by how short it all is. One, I cut some corners, and two, it's still complex. So I'm just focusing on a single list. So think about this as one bucket that we're looking at. There's a global variable here, bucket, that basically points to the first element of that bucket list. Every element has a key value and a pointer to the next element. There's standard sort of stuff, right? And here's the push operation. The push operation pushes a new element into the, or pushes on the front of the stack. So our goal is going to be, draw a picture here. So we have some stack, bunch of elements in it, and we have a bucket that's pointing to the front of that stack. We have a new element E that we want to insert. And so E, we want to arrange the bucket points to E, and then E points to the next element in the list. Right? And it's unfortunate these are two pointer updates, right? And since we don't want to use locks, we have a bit of trickiness to ensure that they're always going to work out fine. So the scheme, this is a typical trick in lock-free programming, is that working good. I'm going to first point E.next to what I think it's going to be pointing to, which is this guy, correct? But at this point, nothing really has happened yet. This E is not even part of the listing, right? So we're basically in good shape. So we actually replace E by square, so that looks the same as the other guys. So this is E, and we're trying to get that in the list. Right? And so now the next thing is the crucial statement. This is compare change. And the compare change is one of these atomic instructions, like test and set. We've seen a couple of them now. We saw them in the last week's lecture too, right? And so the game we're going to want to play is, well, we can update the bucket, correct? And if pointing to E, if it's the case that next is still pointing to the same place the bucket is pointing to, right? Because that means that everything is still in, we're going to insert it in the right place. So this is compare exchange thing does two things: compares these two pointers, and if they're the same, it atomically switches this pointer to point to this one. Okay? So if the compare exchange is successful, then boom, the pointers are in here. Right? Now what could have happened? Right? Why might it fail? Well, operating system a little eager about. So let's save energy. So let me.
Yeah, click the lock on the
Oh, password in front of you guys.
Oh, we know how many characters long.
Oh yeah. Right. So what could have gone wrong? Well, the thing that we have to worry about, there could be second for trying to do exactly the same thing. Right? Then there would both would compare change. And so both will be pointing to this guy, right? And but is going to go first, right? So let's say the top one wins, and so he actually is successfully eliminating a bucket, right? Now the second guy is going to go, right? The down compared chain is going to fail because the bucket actually is not pointing to the next, his next anymore. It's actually pointing to somebody else. So that chain is going to fail, right? And he's going to go to again, and then he's going to try again. Right? And then the whole operation again. In fact, this thing is going to be pointed to here, correct? And then, there will be success, and bucket will be pointed again. Does that make sense? And so this is sort of standard trick, where basically you have to do 2 updates. You sort of set it up, you do the first one in a way that's not visible yet, and then you use the second one sort of as the commit point, and you check whether you actually were successful. Right? That make sense? And this is cool, right? Because from the lookup perspective, the guy reported actually was fine. It doesn't have to have any locks either, right? You just start the bucket and just walk down these pointers. And as long as the pointers are correctly maintained, then we'll run down the list and we'll run down the stack and find whatever it's looking for and just look for it. So we don't even have to modify lookup at all, and it will just work out fine. Right? The only tricky part is basically pop and push. And pop is basically the same thing as push in this case, right? Because we're going to maybe stack, so it's a little bit unfair. And so it's pretty straightforward. Now, to do the same trick for single link list is slightly more complicated. You can do it. And it actually basically has the same key idea in it as actually is stack. So we're not going to really talk about it. Yeah, go ahead.
So what's the right way to think about how compare exchange is implemented? Should we think of it as like it gets exclusive access on the cache line, then does the read and the compare and the write with exclusive access?
Yeah. And actually, this works really well, right, in today's machines where you have per-core caches. You basically fetch that cache line, these 2 cache lines into your cache. You're basically locked in. Blocking really means you just ignore all, or you delay all cache coherence protocol messages until you have performed your instruction.
Right.
And then you're basically releasing them.
Yep.
And so actually this whole atomic construction, so the atomic construction itself is actually very inexpensive, right? It's just 2 operations on your local cache. The hard part, of course, is fetching the stuff into your cache. Or the expensive part. Does that make sense? So if you think like the compare exchange or atomic instruction are more expensive than regular instructions, today's hardware does not mean true. It's equally expensive. Cheap. Yeah, right.
How do you ensure that multiple cores don't start putting duplicate information into your hash table? Like if the guy searches it, decides that he wants to add something that's not there, and then
somebody actually inserted it before. Yeah. So the way to do that, presumably, the way you arrange this is instead of so the maintenance of this list will be all lock free, but when you get to the key value pair, right, where you want to, when you need to take a lock out, you want to arrange that there are no duplicates. You got to be very careful. It takes another step of carefulness. I can talk about it. Yeah.
So this looks like it would work great on few cores, but if a lot of cores are contending, we have absolutely no control over who is fighting over the bunting cache line. So could it actually perform worse than a scalable lock solution?
No, it generally won't. Scalable lock, it's always about, we're always talking about single cache lines. Right? It's going to be very, okay, we can make the cache, okay, so there's a couple things to point out to this, right? First of all, you can make the hash table bigger, and that way you reduce the chance of collisions, right, being on the same bucket, and therefore get a lot of parallels. And also to keep the list very short, so that's double advantage, right? And then that's the trick that people play. And so one of the hard things actually is how to resize these hash tables. So you may want to dynamically resize the hash table. Right? And it turned out that is hard. And we could certainly talk about it, but it would take a little while to explain. But people have come up with algorithms to sort of do lock-free hash tables. It's not clear that's worthwhile doing, right? So I don't want to really talk about it. We got a big bang for the money though, right? By doing this, because basically we don't have a single lock in the whole hash table anymore. We can control how much contention there is by picking a decent hash table size, and therefore we're basically pretty good. We get most of what we want. All right. in some sense, the hash table is the easy case because of this. We can pick the hash table to avoid contention, right? And so probabilistic, there might be still some contention, but it's going to be probabilistically very, very low. Right? So in some sense, we sort of achieved here our goal. As long as we have a good spreading function and the hash table is big enough, we're going to avoid most of the necessary sharing. Right? So if you and I are looking for different files, it's very likely that our files are going to be sitting in different bucket lists, but we're going to be in great shape. Okay. Now it turns out these 6 lines of code, whatever, these couple of lines of code actually have a bug. It's pretty interesting, but it's actually wrong. Well, it's right to some degree. You would still have to do this, but there's a little bit. There's one more twist to it. So let me talk a little bit about it. There's actually a race here. It's a pretty famous race. It actually has its own name. It's called the ADA problem. Race. And it has to do with reuse of memory. Let me sketch it out for you. So let's say we have 2 cores, 1 and 2 in the kind of timeline. We have a link, our list, the 3 elements in it. A, B, and C. And we have the following scenario. Let's say the CPU 1 is to pop off A from the list, right? And so it goes into pop, gets to this compare change instruction. Exciting moment. So it gets to the exchange instruction. It reads, E next, it reads E, it reads bucket, right? So everything's there and just has those values, and calls compare change. Right before it calls compare change, the actual execution curve then is changed. The second core gets to run. The second core, of course, is an unlikely scenario, but it could happen. The second core, what it does, it actually pops A and B off the list. It pops A and B, the second one. So we have a new list, where the fifth points to C. Then, this is a very unlikely scenario, but then it turns out that core 2 allocates more memory and basically reallocates A. Right? And so basically it reallocates A. It's critical new key value in A, right? So A is actually very different from the A that this guy is looking at, correct? Sticks it into the queue. A, or pops it at the beginning of the stack. Right? Now we have this queue again. Right? These values, this pointer is pointing to the same A element. It points to the same address. It's the old A, right, from the previous inclination before the read. And that happens to be the same address, of course, as this A. Right? And so the compare change from CPU1 is actually now going to succeed. Right? And so it's going to pop off this A off the stack, which actually has a completely different A than the previous one, right? Because it was already popped off from the stack by actually core 2.
Yeah. And then it's going to write B to the address of B to the top of the stack, right?
Yeah. All that bad stuff is going to happen.
B is not even allocated.
So you ever see what the problem is? Basically, the A gets, you reuse A, correct? A is reused before actually, core 1 was actually done with A. And which to me also suggests the solution to this problem. And the solution to this problem is actually to delay freeing, correct, of the actual freeing of this A until there's nobody in the push and pop instruction or in the push and pops anymore. Correct? Does that make sense? And so the solution to this problem delay freeing. We'll talk a little bit about different schemes of doing that, but they almost always are performed where you divide time into epochs and you delay freeing an element into some epochs later, in the same way what the graph cache was talking about, so I'm going to talk about it in the context of graph cache. It's the same sort of type of solution. Everybody clear on this? And this is, of course, a very, very nasty mix. Right? A very likely one, extremely unlikely one, because what one part doesn't do something for a whole period of time while another core does a whole bunch of stuff. And the principle is right, it's only wrong because of memory reasons. Okay? You can imagine how hard it is to track these down. Or not track it down at all. And so this is like, again, the warning, like you should really not do lock-free programming until you're really sort of an expert in it. Then even better to actually have somebody else do it because it's complicated stuff. Okay? Okay, so even actually implementing a current hash table, which is sort of reasonable, falls in the category of more simple things, is a hard thing to do. Right? I mean, you can imagine implementing lock-free balanced trees or any other more sophisticated, complicated data structure that you know from the algorithms classes that it gets pretty bizarre very, very quickly. In fact, like red-black trees are notoriously difficult to actually parallelize. Partly because like, if you need to rotate, right, you need to really have to have the grandparents involved, the parents involved, the children involved, and like there's 5 or 6 pointers that all need to be updated, and you basically have one atomic instruction to update one pointer. And so it's an exercise in sort of your hands behind your back trying to get something done. Okay, so that's that. So we're going to talk a little bit about a couple other cases. So even for data structures where they have sort of the length itself is sort of necessary share, but what is necessary, it's a bit of a complication to get there, but you can totally do it. In fact, a lot of the advanced operating system or stable operating system, operating system, going to do a bunch of that kind of stuff. Another interesting case is like one that actually is sharing, right? Really sharing. And what do you do then? And the good one that always is a hard one is reference cache. Talk a little bit about reference cache. And the paper proposes a particular scheme from our reference cache. Right? But before diving into that scheme, we'll just think a little bit about it. In general, what it takes to sort of get a reference count to work. Well, for solution one, right, for any reference count is to just take a lock, acquire L, whatever, implement the reference count, right, that cross, release L. Right? And in fact, you can think about like this is what you do in Josh, right? In fact, except you take the lock for the whole kernel. And then you're somewhere inside, at some point you definitely implement your PP info or whatever structure that has a reference count, and then you release the lock, right? And so this is the JOS version is even worse at this, right? Because the critical section is huge. Well, since the kernel is so small, the critical section is not very long, but certainly longer than a single instruction, right? So this is a single reference count. Again, this is a block where the critical section is a single instruction. And even those turns out can become scaling problems. For the same reasons as in the previous paper, correct? The hard part is actually not updating this reference count. The hard part is actually acquiring the lock. If the lock is not a scalable lock, the cost of actually getting the lock is very high. Can be very high, correct? So this is not a, and so it turns out it is totally possible to construct benchmarks on, we did this a couple of years ago, on Linux, where if you have to pickle some of the reference counts in the Linux kernel and basically endure a complete collapse of performance. And then the benchmarks can generally a little bit better. It actually doesn't use a lock, but it uses an atomic increment. So the next plan is to use atomic increment. And most hardware like x86 has an atomic instruction to actually do increment of 1 or any value of the particular cache. That turns out to be basically no much better, right? Because instead of being dependent on the lock, it's actually going to be dependent on the cache line that holds the reference count, which actually has the same expense, in terms of fetching it from some other form, right? So whether, the cache line that actually holds the data is contained or the cache line that holds the lock is contained, it doesn't really matter. As soon as one of them is contended, your performance is going to collapse if that particular lock happens, if that particular counter happens to be in critical path. So, and this is a little bit of a nasty issue, correct? Because the reference count is there for good reason. Right? Like, you need to, like in your TP info structure, you need to count like how many people actually have this each map. And one that actually reaches 0, you want to release it. Right? And so you do need some mechanism to actually do it. So it's not like, sort of the for a core queue case or whatever, you can just remove the queue. There's not much left to be removed anymore. It's the same integer at this point. And so the trick that you can play, correctly, is it's the same as we did before. So very good. Well, the way we're going to do it is we're basically going to have 3 operations on this reference count. We're going to have key, we're going to have deck, and we're going to sort of split deck up. Very normal. So for example, in Dosh, when you implement the decrement, the ref count basically checks at 0, and 0 does the 3. So the game that we're going to separate out actually is 0. And the reason we'll find out in a second why. Then the other game we're going to play is that we're going to instead of having a single integer representing the reference count, what we're going to do is we're going to have actually n integers, 1 per 4. I'm just going to assign a single scenario. Oh, we're going to count 1. And what we're going to do, an equal decrement, is just going to operate on the per core entry. Okay, so if you decrement the PP info, if a core 1 decrements the PP infrastructure, it actually just updates its reference count. Right? So it's going to be R1, R0, R2, etc. Okay, so this is good, right? Because now every core basically can just update, increment, decrement the reference counters independently of any other core, right? And there's no contention. Of course, we have to make sure that all these counters are on separate cache lines. But if they're on separate cache lines, then there's no fault sharing, then this is going to work out pretty good, right? Now, we have a slight issue. We do have to check once in a while that actually things are 0, right? And so this is why we're separating out 0. You can imagine like delaying this and sort of periodically, going through and sort of check, sum all these guys up, right? And see if that's 0. Now, to make that work correctly, of course, we need blocks per, bucket or per sort of per counter. Right? Because then basically you can get, take the count, take the lock, decrement, increment, release lock. This is per core lock. Most cases uncontainment, so we know from previously that it's extremely cheap. Now, the 0, if you want to do the 0, right, you go through and through acquire all the locks. Right? At that point, nobody can increment and decrement the counter anymore. So it's perfectly safe at this point to actually add up all the values, right? And basically see if it's 0. And if it's 0, you free it, and if it's not 0, then release all the locks and people can keep on going. Make sense? So basically, what we've done is we've made ink and deck basically really cheap at the cost of making a 0 very expensive. Right? But maybe often that actually is probably basically a 0 we could run if we wanted to periodically. Right? Because it's often not the case that we're really that eager to get our memory back. Right? Presumably, hopefully, there's a little bit of free memory enough floating around that it's not necessary that instantaneously we need to get the memory back. And if we're in a situation where we're like, then it's not bad, then we can go and sort of do it on demand, but we can typically batch this. Okay? Make sense? So, what's the downside of this solution?
Well, it's not really clear when to call this 0, and if you just have to do it periodically for like all the reference kind of things, it's not going to become expensive, or you might have to delay a long time, very often.
Yeah, so that's certainly one problem. What is another? I think there's more even simpler. You're thinking already one level deeper. If you have a lot of reference counts in your kernel, like every PP infrastructure has a reference count in it, right? How much memory are we going to use? Lots. info structure in total, right? Your reference count is going to be whatever. If you have 100 cores, it's going to be 100 cache lines. Cache lines is 64 bytes, so it's 100 times 64 bytes, right? Per PP info structure, which basically contains nothing, right? So this is extremely, furthermore, it's going to, so it's going to be expensive in terms of space. In fact, I mean, we have a lot of reference counts, like in, for every, we do play this game for every, so it's, 64 bytes times 100, right, for one PP info structure. And if we have a PP infrastructure for every page of memory, physical page of memory, so you're going to consume a ton of physical memory just to keep track of the reference counts, right? And so in here, basically,
Can you put multiple ref counts from the same core for different things in one cache line?
yeah, you can play games, right? And, in some sense, this is what graph cache does. Right? I mean, it's part of the paper today. The paper today has two pieces to it. One is RadixVM, sort of a parallel to the memory system, but it heavily relies on reference counters for the same reason that PP info has a reference counter. Right? And so RefCache is a solution for this. You can think about all kinds of different. Once you're faced with this problem, you can start thinking and come up with a solution. And so let me talk about the RefCache one. You can evaluate whether you like it or you have a better plan. Perfectly fine too. In fact, if you have a better plan, you can write a paper on it. I believe it's the best reference counting scheme so far around. This is also a huge literature of reference counting, which is amazing. Really. It's a basic computer science thing about counting plus 1 minus 1. How can it be that on this paper written on this topic? But it is. So the way RefCache works, right? So the RefCache plan is to have an object, and it actually has a reference. Of course, it has a lot of and this is the top of 1. And in between, it has a whole bunch of other information related to actually the object. Think about this as like one PP info thing. And then the plan, so these are just sitting there, and then there is every core will have an array like this, slots and stores, like a little water. And every core basically has a little cache. And you can pick the cache while you like. And so let's say it's a little cache. And in that cache, it maintains objects that it cares about. So here might be O1, and for O1, it maintains delta, which is the index index applied to O1 at that particular core. Right? And so another core might have also a little cache, and it might have O1 and O2, and a delta for it changes, where the delta is the index index. So you do 2 inks, the delta will be 2. You do an ink in the deck, the delta will be 0. Right? And so, like before, the previous scheme, it's pretty cool because the ink index can just operate very at per core speeds, basically. Right? The reason that it's cool to have cache, what's the advantage of having the cache? The goal is not to play this game for every reference counter, because it's very likely that every reference counter is actually equally contained, right? If you have a scaling bottleneck, it's typically the case because there's one counter that is really the problem, or a few small counters in different subsystems. Right? And so the game we're playing here is basically, you take some cache out, so it basically contains all the containment counters. And as any good cache, you throw out the guys that actually being least frequently used. Which is good, right? Because that's less than counter. And so basically what we're going to find out, and you can pick the cache what you like, but you can at least know the amount of space, right? The amount of space now is going to be equal to the number of cores plus, what the size of the cache. But not multiple anymore, right? Before we had the number of cores times the number of counters we have in the total in the system. So this dynamically, adjusts, to like if one counter gets contained for a while, then it won't be in the cache. If that counter is not contained anymore, it will disappear from the cache automatically. Okay? And so, int exec, play the same game, and also, basically updating local things. Then the zero, a little bit clever, because you don't want to really run zero every time, your rate's zero. In fact, the way it works is that when decrement, you saw in the paper, the decrement reaches an object with delta of the good. And so the weight is zero. Let me focus on this. The weight is zero is implemented. It's basically every, the time is divided in n blocks. In the game that we're going to be playing is like, think about the epoch is like 10 milliseconds, like some timing interrupt, right? Or like every same rate that the schedule runs. You can pick any time you like, something. And every 10 milliseconds, we're actually not going to run a zero as a global operation, but basically every 10 milliseconds, one of these guys is going to bit or basically flush its delta to actually the object that actually has the value in it. And so basically what it's going to do, it's going to take a walk out of the reference counter, apply its delta to the reference counter, and then be done. And we're basically doing every epoch, we're going to do that. And presumably what will happen is these guys will be spread around a little bit during the 10 milliseconds where they're actually doing these updates. But they're not going to take that back. And we can pick the 10 milliseconds large enough that we can basically batch a lot of these things and decks. Then when a core, applies its delta to the reference count, and the reference count actually happens to be zero, then the observation is, well, you can't really remove it, right, at this particular point in time, because there might be other deltas floating around in the system, right, that happen to be flushed here. So this might be zero, but we don't really know for sure. At that point, we can't do anything at all. And instead, what as zero does, it basically pens this for review. Right? So it pens for review to epochs later. And so let's assume that for two epochs it actually stays zero. Well, that means complete epoch has passed, correct? And that everybody had a chance to basically flush the deltas to the global counter. And so after two core epochs, we know for absolute sure that everybody went through this epoch, flushed all the changes, and if the counter is still zero, then it must be zero. Right? The true value must be zero. And then that one we can just read. Right? And it means that there's a delay of maybe 20 milliseconds before we actually free, but then we free. Okay.
So, can there be a scenario where maybe it was zero then, and then it went to one again, and then it was zero again? In that case, we probably.
That's a very good observation, a good question. This reference count is based on the assumption that if you reach zero, it will stay at zero. Right, so if you decrement, so like say you take a PP3 page, and once it's unmapped from all the process, virtual memory mappings, it will be zero, correct? And it won't go up in zero until it's reallocated. And
Well, I think that's actually the case I meant.
Okay.
I think I meant the case where it's not actually zero yet,
Okay.
because there's some deltas there. But one core observes that as zero, and then another core flushes it and brings back to the real one.
Yeah, so then basically when you're out, so this is a good point. So after two out, that helps you review. If the reference count is not zero, then you keep going. There's nothing, you don't do anything.
Right, but it could have become false zero again, right?
It could, except after two epochs, everybody has flushed. Once it reaches zero, for true, and after a more complete epoch, and everybody has flushed the changes, it can't go back up. Like once it truly reaches zero, it will never go back up.
Right, but what if it never reaches truly zero? Anyway, we would.
Okay, well, maybe we should. Well, let's say they take it offline. It works. Well, we think it works.
So I think also important is that that the first person to reach the zero puts it to their epoch queue.
Yeah.
But that's in and of itself a form of a lock. Like how is that maintained?
Basically, the review. So you take the lock out on the operation. Okay, so what will happen is the first guy that sees that it thinks it's 0, they'll put it under the view queue of this particular object. But no other core will do it because we'll be able to see in the global object that already it is under the view queue. And so there's a bit of cache line contention and bouncing for that particular operation, but only for that operation. So in the case of reference count, it's not possible to eliminate all sharing, right? Because the whole damn thing, reference count is there is to actually do its own sharing. So this is basically a scheme to push all that sharing into sort of like one corner, so that it maybe compensates like you read in the index if you don't pay for it. Yeah.
I think there was also a special case in the paper where if the reference count changes at all while the object is queued up for review, then the review is put off for another 2 hours.
Yes.
Yeah.
So we're waiting for
This is what I meant earlier. This is what I meant earlier. That if you decide it's not 0, you push it out.
Okay. Then, yeah, then.
Yeah. Thank you. Yeah, so the paper scheme is even more complicated than this, right? Because in the paper scheme, you can actually reapply a reference count. And they're called weaker references. I'm not going to talk about that. Basically, sort of an extension of this basic plan. The main goal is to get sort of a sense about what it takes to parallelize an operating system, sort of to the extreme if you really want to scale with large reports. We're all good at this? Okay. And the funny thing here of all this, at least it took me by surprise when I worked on, spent quite a number of years thinking about these kinds of problems. Still thinking about these kinds of problems. Basically, a single reference count can actually be a scaling problem. This is a single instruction. Right? So the kernel is 50 million lines of code, right? And of course, not all code paths are 50 million lines of code, but there are code paths like a single contained reference count can basically kill performance. And that doesn't, of course, most reference counts are fine. There's going to be no problem at all, but you just have to have one, and you're in trouble. So you can be in trouble. Like in some application, like an important application triggers it, then these guys will go off and figure out how to fix it. Okay. Okay, so even reference counts are exciting and interesting. Any questions about this before I move on to the next step? So this is sort of giving a little bit of illustration. These are the level of sort of detailed sort of data structure hacking, like what kind of things you sort of need to do to make things more scalable, and what people do in practice. And then but now I want to talk about like one subsystem. We haven't really talked about subsystems. We've sort of thought about single little data structures. The subsystem I'm going to take is the VM system. Partly because you guys are VM experts. It shows up in the labs everywhere, it shows up sort of crucial components. And so it's an interesting thing to think about. And there's a couple things to point out. First of all, VM offers, so you're going to want to focus on map, min-map, and hateful. Right, and actually SIG, right, map and min are going to be supported, but in Josh, actually in one place where Josh is more functional than XV6, you have a map and min operation, right? And so, the typical operating system will maintain, right, the page table per process. And so, in the case, if you're maintaining, so it's like in XV6, right, or Josh, basically a page table per environment, right? You load something into the CO3 when you switch. So when you do a map and map in different processes or in different environments, will they content? Should be possible to make them not content. It should be, right? Because every process has its own page table. If the map and one-map are in different processes, they should operate in different page tables, and there should be no issue whatsoever, right? It should be reasonably straightforward. Now, they may, maybe they map the same page, the same physical page, correct? And then you say, well, and then maybe there's a contention in the reference count that goes around with the physical page associated with. But let's assume in the case where they each have their own physical memory, their own page table, there should be basically no contention, correct? In fact, most operating systems today, this is exactly the case. There is no contention, it's parallelized beautifully, and no sweat whatsoever. The case that the paper's worried about is we have a process, we have multiple processes, and so each process has their own page table, okay? Because they have their own address space. It's all good, but processes may be multi-threaded. You might have multiple threads in the same address space. Certainly on a scalable operating system where you're running on a multi-threaded server, this is a scenario that can easily happen for every multiple. And so the problem that can actually appear is that, and this is the way we observed it initially, and also people in the industry have observed it many times, is that if these threads actually deallocate a lot of memory, they actually make nap and in-nap calls. Right? Because they have to get more memory, you have to update the page table to actually put that memory, free memory, your new physical memory into your address space. Right? And so, in the way, for example, in Linux, this is implemented in almost all operating systems I know of, there's basically one big block on the page table. And for many reasons, we'll go into in a second. But so it's easy, if you have a lot of threads, trying to update their address space, their shared address space, that this block is contained. I think that's when people observe this in practice. Now, it turns out, of course, if you observe the problem, there's a couple ways about this. One is to say, well, I'm going to rewrite the VM system, right? Which is what the paper basically does. And of course, the first thing to observe that is that's actually a complicated thing to do, right? I mean, you know now how much you write a very simple VM system. And even then, it's not easy to write a VM system correctly, right? So let alone if we go back and say, okay, well, I'm going to parallelize the VM system, and that's not it's not a couple days of programming. So the other way out of it is to say, well, I'll never free memory. Right? So I just allocate more memory, but never free. And then at least I don't have contention on free, right? I basically hoard all physical memory. And that's and I think people who have observed that basically that process gets so big, if they do that, it's also not completely ideal. So another option is to make your malloc library extremely clever. And most malloc libraries are actually extremely clever. So scalable malloc libraries, or there's a whole bunch of malloc libraries out there that try to do a good job. Another solution, most people do in practice, is to say, well, good, I'll do that. I have my multi-threaded process. But actually, I'm not sharing that much memory between my threads. What I'll do, I'll rewrite it like in processes. Right? And all those processes have their own page table, and boom, I don't have contention anymore. Right? And whatever sharing I have, I'll have a couple pages, and I'll map them in each address space. Right? Or is the rewriting the application to avoid this particular kernel block. Right? Makes sense? This could be a painful exercise, maybe a very easy exercise, depending on the complexity of your application. Right? In total, these are all fine solutions. So the paper takes a little bit more of a sort of extreme point of view and says, it's all making programmers' life hard. The right solution is to actually parallelize the VM system. And in the same way that the buffer task has been parallelized, the name task has been parallelized, the scheduling has been parallelized, we should also parallelize the VM system for multi-threaded applications. Now, it turns out that the VM system is a hard one to parallelize, which is one of the main reasons why it hasn't been done yet, right? And so, there are a couple of things that make it hard. So let's talk a little bit about these challenges. So what are the challenges? Well, one is actually ref downs. The ref dash gives us a solution for that. Right? And the ref downs are the ref downs in the PPA function. Those ref downs. The second is we need some index structure for maintaining the page state. Some index structure. The third one is Namely, if you do an unmap, and unmap returns, a system called unmap returns, it should not be possible for any thread after that to access that page. It should be removed from the page table. And so you got to make sure that if the unmap is done, then there basically no other thread can access the page. So it means like page faults, you got to be careful about worrying with page faults and apps and index. So these are the three challenges. So the paper addresses all of these three challenges. So we know about the rectangles. Let's first talk about the index structure. Okay, so the index structure. In some ways, this problem is going to look to you as completely artificial because, in fact, you have a solution to this in Josh. Nobody uses that solution in practice. That's another different sense. So what we're going to do, Rick, is the goal that the paper has is if we, so let's just get some information where we actually can get parallelism. The goal that the paper focuses on is the case of maps and unmaps of non-overlapping memory regions. So if you map a page in one thread, and map another different page in another thread, the goal should be that these two operations can proceed in parallel, because in fact they have nothing to do with each other, right? They're talking to different parts of the address space, so it should be possible to parallelize those. For operations that have overlapping memory regions, the paper says like, oh, too bad, we're not worried about that problem at all. Right? Because that's basically real contention, and we have nothing to say about real contention. It's basically particular case. We at least want to make sure that when there is no contention, there is actually no sharing at all, we actually do get parallelism. Right? And so this falls completely in the whole line of work that we've been talking about the whole lecture, where it's basically avoiding unnecessary sharing. Right? Because two maps and maps work in different regions, there is no sharing, so we should avoid any unnecessary sharing. Okay, so the easy way of doing that is, right, if you represent your index structure, your page table, as an array with index by page number, right, from 0 to n minus 1, then you're automatically going to get no contention, right, no sharing. Because like if thread 1 operates in page, virtual page number 0 and the other one is number 1, and you block say it needs to be different structure in different array if it's available, we're automatically going to get parallelism. Right? So how do you represent your page table in Josh? It's a little wild back too. We use arrays. I didn't realize you guys don't do anything special. Nobody ever paid any attention to it. It's just an array. You index with it and done. But what's the downside of an array?
It's big. You need to have something for every possible address.
Yeah, or every, so if page is 4 kilobytes, right? And we use a large swath of the address space, then we're going to have a lot of entries in this array, right? That's slightly unfortunate. Particularly because how much you can use actually with the address space. If you have a 232, let's say 2264 is more interesting when you have a 64-bit machine, right? It's 36. Typical application, how much would you use it? How big are your applications in Josh? How many pages do they use? Do they use the whole address space? No, I don't like 5 pages or something like that, right? Whatever, 1 page for instructions, a couple pages for instructions, a couple pages for data, and a couple pages for stat, right? But that's not it. Now, Josh applications are a joke, right? They're little, tiny little apps. Like, the X window system is not going to take your whole address space, right? Huge, gigantic gaps in the address space. So, no operating system, no sensible operating system represents the page table by an array. It's just wasting memory. So, the obvious thing to do is say, like, we know all about this from, like, data structure courses, use a better data structure, right? Like something, that a tree, right? any sort of balanced data structure is going to be fine for any balanced tree. Pretty good, right? Because basically, you're going to represent swaths of the address space by a single entry in this tree, and you're done. And so that's what every sort of sensible operating system does. Linux contains a black tree, other FreeBSD uses an AVL tree, and so you can imagine whatever your favorite tree if you like. And so that's the common action case. And so you think a little bit about it, then it makes a lot of sense why there's a lot of address space, because basically the current operation of balanced trees is really difficult. A little bit earlier mentioned this. For example, a red block tree, you rebalance, because the reason why that happens, Greg, is you do an insert on this tree, and there's lookups going on too, but the insert, at the point you do the insert, might require you to rebalance the tree. And so you have to change the shape of the tree, but while you're doing that, there's a lookup going along, right? And you got to make sure that the lookup actually does find all the mappings that exist. But while you're like updating these 5 pointers, like the grandparent, parent, the children, to rotate, this red and black tree, you might run the risk that you look up, go down some branch that you just moved to some other part of the tree that the lookup already passed. So this turned out to be so basically concurrent balanced trees are difficult. So that didn't sway us from trying anyway, and in fact we did, and so we used like a concurrent skip list. It seemed like concurrent skip lists are the ideal data structure for this kind of thing. They're pretty simple, and you could do well. And so we replaced basically in some VM system, we replaced the balanced tree that was there with a concurrent skip list. That's a nice structure too, everything bingo. And to a great surprise, it didn't scale at all. And it was a little bit nasty. And in fact, you can see that in figure 4 in the paper. I don't know if people have it. Not figure 4. All right, so in figure 6 is the problem. You see actually in figure 6 that the concurrent skip list actually, concurrent skip list actually scales great for no writers. So nobody inserts anything in the tree while you're reading. And that, you would at least hope that is true. Right? But it turns out in a small number of writers, in fact, there's only one writer is the green line, and 5 writers is the blue line. So there's 5 cores, there's nothing else than insert, insert, insert. And in this particular case, there's 75 cores that are doing reads. And if you look at this graph, it basically flattens out very, very quickly. Right? And so the amount of parallel speed up you're getting out of this skip list is tiny. In fact, it gets suddenly it actually goes flat at like 10 cores basically. And of course we thought like we had a bug in our skip list and we didn't know what we were doing, and that's probably true too, but after a while we convinced ourselves that this is okay. And the problem that was going on is exactly the same problem that we have seen over and over now in this lecture and in the previous lecture. What happens is that in any balanced tree or any index structure, right, this kind of form, it's very easy to explain what actually goes on. So there's the root, and what happens is 5 writers are going through, operating in different places in the tree, right? So the writers actually manipulating different keys than actually the readers are looking at. And so these 2 operations are principally independent. But what happens, of course, these writers, once in a while, update the index nodes. Right? So when they update their index nodes, they're going to fetch the index node, put it in their cache line, and modify it. Right? Then the readers are going to come along, and they're going to fetch all that, that tab, those 75 readers are going to come along, and they're going to fetch that node from that one guy that just wrote it, correct? And boom, we got the same problem back that we have with these non-scalable blocks, right? And in fact, this is exactly what's going on. With a small number of writers, there's enough index nodes being updated that there are enough readers banging on it to actually fetch them that basically the performance collapses. And so one way to think about this is that basically there is sharing going on where there was really no sharing necessary, right? Because the lookups were done in different keys, the inserts are different keys. The only sharing that's going on is these damn index nodes And we didn't even ask for them, right? But they're only there because we want, like, login and stuff. Make sense? So, okay, so this basically this stretched off all down the streets from the list of potential solutions, right? And the rates started looking really good again. It was the only one we knew how to do it. But we didn't want to pay the cost of the rate. So basically this solution, it's pretty straightforward. What you do, right? You just take a radix tree where the index is conditioned on the value of the key. Right? And so as long as the keys are in different places, then you're going to go with different errors. So the next, the next script needs to be, do a okay, so let me stop here because I'm running out of time. I'll pick this up on Monday and finish this off. There's a couple more points I want to make, and then we'll start talking about VM right after. Okay? So happy Thanksgiving. I guess most of you will probably be hacking on Lab 6. Right? And if you're doing Lab 7 for your own project, you always sort of progress report by tonight. If you do Lab 6, you don't have to send us anything. If you do Lab 7, please send us a little bit of an update on where you are and how things are going.